All right, so the last lab that we're going to talk about is enthalpy of neutralization, where we're really just taking a simpler reaction as HCl. We know that HCl is a strong acid, so we can really treat it as H plus or H3O plus, reacting with OH minus to go into H2O. And our job is to figure out how much heat and then turn that into an understanding of our Gibbs free energy for this, as well as the entropy for this reaction. So we're going to do this twice. We know back from our first law of thermodynamics here that any heat that is lost plus heat that is gained is equal to 0. So as we do this and we take our H plus OH minus is going to go into H2O, and we do this in our calorimeter, which is our nice little double pack of styrofoam cups here. If we take 25 mils of my 2 molar HCl, that was intentional, and I add it to 25 mils of my 2 molar sodium hydroxide. So this is my hydroxide, and this is my H plus, and each of these are 25 milliliters of 2 molar. What I'm going to end up doing is, in fact, immediately diluting them to 1 molar with the note 1 molar, remember, is standard state. And we like standard state. We want to calculate standard states as we do this. So here, when we do this on our reaction, our volume of solution is going to be 50 milliliters. We're going to add those up. Temperature initial, you are going to measure it. It's going to be around 21 or 22 degrees Celsius. Temperature final is going to be on the order of about 35 degrees Celsius. And I'm just going to make these up and call this 13 degrees Celsius. When we do this, we're going to have the mass. If we have this density, and I have a volume of 50 milliliters, and I know this has a mass of 1.04 grams per mil, I'm going to take and get a mass of my solution of 52 grams. I know that my heat Q is going to be mass times specific heat capacity times delta T. This is an exothermic reaction. As H plus reacts with OH minus, it is going to generate water and heat, and that heat is going to go into all of this stuff that is inside of this aqueous solution, which is in fact 1 molar sodium chloride and the water. And to answer your question, yes, you can throw that down the sink. It's 1 molar sodium chloride. So our heat Q will be mass, which is 52 grams, times C sub S, 3.87 degrees C per, 3.87 joules per gram degrees Celsius, multiplied by your delta T. So I'm going to do 13 degrees Celsius. Again, just kind of making some numbers up. I don't think it's too far off. And I'm going to get for this a value of 2616 joules. I'll worry about my sig figs in a second. We're going to do it for 2 of these and realize that that is the heat that was gained by the solution. We know that the first law tells us that heat that is lost here by our reaction, and it's going to be lost because our reaction is exothermic, plus heat that is gained, that is going to be by our solution. Remember that this is positive, so this is going to be negative, and that has to add to 0. So if I have gained 2616 joules for my solution, my Q of my reaction is going to be minus 2616 joules. I want to know what my delta H is. Remember, my delta H for a reaction is going to be the heat of my reaction. We're going to put this in kilojoules, and we're going to normalize this to the number of moles that have reacted. We can get moles. We can either do water formed or HCl reacted or NaOH reacted. Doesn't matter, it's 1 to 1 to 1. If we do this, we know the volume in liters multiplied by the molarity is moles. Our volume in liters is 0.0250 liters. My molarity is 2 molar. And when I do this, I'm going to get 0.050 moles of the moles of HCl that is reacted. And if I take and I do this now, I can get my delta H. My delta H is going to be minus 2616 joules divided by 0.050 moles. And I know there's a kilojoule for every 1,000 joules. And when I do my math from that one, I'm going to get a value of delta H of minus 52 kilojoules per mole that has reacted. Now it should be on the order of, I think, about 54, so that's pretty good, particularly considering it wasn't a nice isolated system. Now, what is our job for this? Our job is now to figure out what we're going to do with this, because our goal is not to get delta H, that's Chem 111. Our goal is to get the equilibrium constant, a delta G, and a delta S, with a note that our delta G naught, remember naught is standard state, is going to equal minus RT times the natural log of the equilibrium constant, the same equilibrium constant we've been working with. If we think about the reaction of H plus OH minus is going into H2O, which is our reaction here, we've seen something like this before. And what we have seen instead before is not this, we have seen the reverse of this. The reverse of this is H2O dissociating into H plus OH minus. If we wanted to, we could do two waters, maybe be looking a bit more familiar with our nice two arrows, into H3O plus OH minus. If the K for this one is 1 times 10 to the minus 14, then the K for this one is 1 over 1 times 10 to the minus 14. And we can take and find the delta G naught for this reaction, because it is going to equal minus R, we know R, 8.314 joules per K mole. Use the temperature from your room temperature, your initial temperature, and plug in your value right here of K, where K for this reaction is 1 times 10 to the positive 14th. Nice and spontaneous. This one's negative 14. This one is the reverse, so it's positive 14. And you can calculate delta G. Once you have calculated delta G, we can do one more step. We're going to talk in chapter 16 that a delta G, this is our Gibbs free energy, the maximum energy available to do work, is equal to our delta H minus T delta S. Our job in this last part, question 11, is to find the delta S. Well, how are we going to do this? Well, we're going to take delta G from right here. Watch your units. It's going to come out here in units of joules per mole. Our delta H, we know, we got it up above, and it was minus 52,000 joules per mole. Delta G from question 10, temperature is going to be T initial, and solve for delta S. Delta S is the change in entropy, which is the change in order or disorder for our reaction. And so take and do that for this reaction and the rest of this. And in fact, that's it for the entirety of the lab. So make sure you can do that and that makes sense.